Hello, bonjour, bienvenue, and welcome everyone to Perimeter Institute's public lecture series. My name is Emily Petroff, and I'm Perimeter's Director of External Relations. I'm delighted to welcome you back to the Mike Lazaridis Theater of Ideas here at the Perimeter Institute in Waterloo. By its very design, Perimeter Institute was created to be a place to gather and connect, where people can come together, like we are doing tonight, to ask big questions about the universe and search for big answers. This year, we are celebrating Perimeter Institute's 25th anniversary. 25 exceptional years of bringing people together from all paths, researchers, students, teachers, and the general public, to explore the fascinating world of physics. But people on this land have been asking big questions about the universe for thousands of years. The quest to explore the world around us, to piece together our origins and understand the building blocks that make our world, these are human constants throughout the ages. We acknowledge that Perimeter is situated on the traditional territory of the Anishinaabe, Haudenosaunee, and Neutral peoples, and is located on the Haldeman Tract, the tract granted by the British to the Six Nations of the Grand River and the Mississaugas of the Credit First Nation. We acknowledge and thank the many peoples who have preceded us and share this land with us, and we commit to moving forward in the spirit of reconciliation, to acting responsibly and collaboratively to advance the quest for knowledge for the benefit of all. I hope you will join us in this endeavor, tonight and all throughout our 25th year. By the end of tonight, I hope you will leave this beautiful building having met some new people and learned something new. We'd like to take a moment to say thank you to the people who make events like these possible. Thank you to all of our supporters who help to engage and inspire young minds, train and support educators, share science with the general public, and help bridge the knowledge gap in science. If you'd like to join our growing community of friends and supporters, you can visit our website to learn more. For those who are watching the live webcast, please join the conversation online, either through the YouTube comments section or connecting with us as Perimeter Institute on Instagram. If you have a question for our speaker, you can ask it with the hashtag #PILive. And now, it is my very great pleasure to introduce tonight's speaker. As we continue our 25th anniversary celebrations, we're so pleased to feature extraordinary researchers working across all areas of theoretical physics, speaking about some of the most cutting-edge research and latest developments in their fields. Tonight's speaker is an expert in cosmology, particle physics, and gravity, working to answer some of the most fundamental questions about the nature of the universe. Dr. Sarah Shandera is a professor of physics and the director of the Institute for Gravitation and the Cosmos at Pennsylvania State University. She received her PhD in physics from Cornell University in 2006 and held postdoctoral positions at Columbia University's Institute for Strings, Cosmology, and Astroparticle Physics and at Perimeter Institute for Theoretical Physics before joining the faculty at Penn State in 2011. She's been a regular visitor at Perimeter since, as a collaborator, speaker, and a Simons Emmy-Noether Fellow, and we're very pleased to have her here with us tonight to talk about her work. Please join me in welcoming to the stage Professor Sarah Shandera.
Thank you. Thank you, Emily, so much for that very kind introduction. It's always great to be back at PI, so thank you for being here with me tonight. The story that I want to tell you today is the continuation of one of the oldest human scientific stories that we have. It's the story of looking up and looking out and asking, how to make sense of it all. Or looking up and looking out and saying, man, there's got to be so much more out there. And as we've figured out how to make better, more precise eyes on the universe, we've taken this passion of stargazing and turned it into a discipline of cosmology. So the story I want to tell you tonight is sort of where we're at in cosmology, what we know, where we think we're going. So there will be some facts. There will also be some wild speculation. This is actually underneath a math story, right? I'm a theoretical physicist because I really like math. So although what I'm going to show you are pictures, this is under the hood a math story. So what I'd like to convince you by the end of the talk is that we are not only in an era where we have extraordinary amounts of data coming in at an extraordinary rate, but we're also in an era where the modeling, the sharp math tools that we use to make sense of the universe could maybe use an upgrade and maybe a little bit different perspective. So it's a really exciting time because it's full of possibility and full of data to check what we're doing. So let me come to this picture here. I think this is an extraordinary picture because it is, at the same time, so relatable, right? If you were to go out in a very dark sky and look up during a meteor shower, this is what you'd see. And while it's relatable, it's also extraordinary because the precision of the instrument to take this picture, so sharp, right, with all of these light sources, and to actually track that trace of something entering the atmosphere across the sky, that's an extraordinary instrument, piece of technology, and it's also an extraordinary individual who's very skilled to make that image. So this is, what you see in the night sky on average. Of course, just as that camera is extraordinary, the instruments that we use to look beyond just the camera you can hold, are also extraordinary. And so if you were to go out in this night sky and hold up, say, a pencil, and look at just where the tip of the pencil is, maybe on some part of the sky that looks dark, and you were to put the very best eyes that we have technologically on that patch of the sky, what you would find is that, oh yeah, there's more. So this is an image, probably not that patch, I'm sure I didn't get that part of the sky right, but this is an image released earlier this year by the James Webb Space Telescope. So this is one of the most extraordinary instruments we have, right, to see the sky in detail. And what it sees in that tiny, tiny patch of the sky is all of this, which includes, of course, entire galaxies as well, right? So the amount of stuff that's out there is just mind-boggling. The story of this image is actually really interesting. This is something called the Hubble Deep Field. And the story is that, even in the 1990s, we had some pretty good instruments that were on the ground to go out and look out at the sky. But in the mid-90s, Hubble went up into space. And one of the interesting things that happened with Hubble is that somebody dared enough to say, you know what, let's take this instrument, which is so extraordinary and so expensive to use, and let's point it at a part of the sky that looks empty and see what we get. And with enough staring, of course, what they saw was that that part of the sky is not empty. It's filled with all kinds of interesting stuff, including galaxies. That's the Hubble Deep Field. And those patches of the sky have been then since observed with every instrument we get as we get better and better able to look out. So when we make these observations and the instruments get better, they're really doing two things, right? They're collecting more light, so we see things that were faint farther away. They're also looking back in time. And because the universe expands, that means that light's stretched, and so the instruments have to be able to look at those stretched wavelengths of light to reconstruct what was happening. So what's happened since Hubble is that we have increasingly improved these images such that today, when James Webb gives you those images, those are some of the very, very, very first things that were ever formed in the universe, stars and galaxies. And that's extraordinary that we can see that and try to make sense of that story. And it really is, looking back in time to a point when the universe was very young, and especially young in terms of the amount of stuff that was there, the amount of structure. So I want to make the point that the observatories we have today that are releasing data, now, literally this year, are truly extraordinary. So beyond James Webb, I wanted to mention just a couple of other examples. The first of those has to do with the fact that in this image, we see stuff that's pretty stationary, right? You look out, you see the stars are what they are. They more or less stay the same. But the universe is also filled with stuff that happens on fast timescales. So in this example, it's a piece of rock shooting into the atmosphere. But there are many, many events in the nearby universe that happen all the time that are energetic phenomena that happen in a flash. Things are changing, stars are changing as we look out. And the instrument that's designed to make a picture of all of those transient events, those things that happen on short timescales, is this Vera Rubin Observatory and this legacy survey of space and time. So Vera Rubin will make those extraordinarily sharp images every single night. The instrument is in commissioning, so June 23rd, just again a couple months ago, the very first images of this instrument were released, and the science should start in a few months. But the science is the entire sky, every night, at a level of detail that is 15 terabytes of data, right? That is amazing. And in that data, astronomers will find millions of things that have changed, right, from night to night, and send millions of alerts out to astronomers and say, hey, go look at that, go look at that, go look at that, go look at that. And there's a whole industry of people, trying to decide which of these million events do I want to go look at, which do I want to look at, which do I want to look at. So this will be truly, truly phenomenal in terms of understanding the active universe today. That was light. All of that had to do with light. Of course, we don't just see the universe in light, and I say of course, but that's actually really new, right? We have several fundamental forces in nature. Light is one of them. Another one is gravity. And one of the most extraordinary things that's happened over the past decade is that we can actually see, or hear, maybe, the universe in gravitational waves. So the LIGO interferometers can detect how much space bends by the passage, and stretches by the passage of gravitational waves that are released when really heavy objects like black holes spiral together and merge into a single black hole. When the first sort of large-scale detectors of this type were built, they could see pretty far. I don't know if you can tell. This is 100 million light years. So the distance light can travel, right, in 100 million years. The detectors could see about this far. That's really far. On the other hand, it's nothing compared to the size of the space that we've explored, right, or seen, visualized. Those were impressive detectors. They weren't impressive enough to find gravitational waves. That had to wait until almost exactly a decade ago, September 14th, 2015, when the detectors were good enough, instead of seeing this far, to see this far. And that was the first time that we were able to see gravitational waves from the merger of two black holes, so really see the universe in a force other than light. 10 years later, again, just a few weeks ago, the new release of all of the events that LIGO has seen of black holes merging, right, or neutron stars merging, something like 218 events were released. And by now, the distance that those detectors can see is indicated by that line there. So we've gone from this little bitty thing here about 20 years ago to this really big volume now. And again, that's something that will continue to expand as our ability to measure these gravitational waves increases. So this is an extraordinary moment in terms of data. And what we've known for some time, that data doesn't do anything to tell us this isn't the case. I want to summarize it in 4 facts about the universe. This one, the first one seems maybe in today's world, of course we know that, but it actually wasn't that long ago that we didn't know it, that the universe is not in a steady state. The universe is evolving, it's changing. The second fact is, again, quite obvious and yet still extraordinary, that the universe is nearly smooth, but not quite. Right? Especially in the very early times before gravity had a chance to act, it was nearly smooth, but not quite. The third fact, which again we've known for a couple decades, is that the current expansion rate of the universe is accelerating. So something's going on that's sort of driving space apart. And the fourth fact is that most of the stuff that's out there is not what's in this room. It's something new. It's some kind of matter that we don't yet understand. Let me start with the first fact. The universe is not in a steady state. I mean, very roughly speaking, this is a picture of the evolution of the universe with time going this way. And you can see stuff is happening, galaxies are forming. It's not my crude version of the stationary state universe, where it's basically the same, right? As far as you look out, yeah, there's galaxies, they look the same. That's not the case. The universe is evolving. It wasn't that long ago that we didn't actually know that for sure. And the discovery of that fact has to do with something called the cosmic microwave background, which is a bath of light, which is not starlight. It's something else. It's a relic of that early time when the universe was doing something different. And this knowledge, this certainty, is a few decades old and received the Nobel Prize about 20 years ago. But that was the first time that we really knew for sure that the universe was doing something different. It's this expanding, cooling universe, not just a stationary state universe, steady state universe. The other thing that light revealed is this notion of not smooth, right? Of course, you look out, you see galaxies, that's not smooth. But this notion of not smooth had its start at a very, very early time when this cosmic microwave background light was released. And if you take this light that's the same everywhere, and you look at what the tiny fluctuations are, you find that it's apart in 10,000 deviations in temperature from exactly the same temperature everywhere. So this picture is showing you what are really tiny, tiny fluctuations, 1 over 10,000 compared to this picture. That's the degree to which that initial universe was not smooth, a tiny bit. And it's the action of gravity over time that's turned that into really something extraordinary. That not quite is where all the fun is, right? Had the universe been perfectly, perfectly smooth, none of this amazing stuff that we're seeing with JWST, with gravitational waves, none of that stuff would have existed. We would have had a pretty boring universe. So the not quite is super important. The third fact, and this again is a Nobel Prize-winning fact, is illustrated in the envelope of this picture. So the interior of this picture is showing you the history of the universe in that not smooth part, the really fun part, right? So little fluctuations in temperature and density that grow via gravity to become all of these complicated structures we see today. The envelope of this picture is showing you what happens if you smooth all of that structure away and you just ask of all the matter and all the energy that's there in the universe, how does it affect the expansion rate of the universe? That expansion rate changes as a function of time. And this uptick at the end has to do with the fact that very recently, that expansion started to accelerate. We've labeled the stuff that does that dark energy. And if you ask how important is dark energy today in the expansion rate of the universe, it's incredibly important. It's like 70% of this pie. We call it dark because, well, it doesn't emit light, right? We're not exactly sure what it is. It's the dark energy. Important enough for a Nobel Prize, but not something that we really understand yet. The fourth fact is also on this chart. Not only do we have this dark energy, which makes the universe expand at a faster rate, we've got this stuff called dark matter, right? So if you ask, of all the stuff that acts like matter out there, right? It's not this dark energy stuff that gives you accelerated expansion. It's also not some radiation. It really acts like matter. How much of that is stuff that we understand, the stuff that we're made of here in this room? And the answer is not much. Most of it is this other stuff, dark matter. Dark matter, why is it dark? Because it doesn't emit light. So we don't see it in the same way that we see those galaxies with JWST, for example. So these are 4 facts about the universe. They're facts that we've known for decades, all of them. And if you turn those into scientific questions, what's going on in the universe, those 4 facts give us 4 really enduring puzzles. For decades, we've asked, why is it not a steady state? That why, for scientists, how did it get started? What's the initial state? Is that an initial state that makes sense, that I feel is natural? And where is it headed, right? What is the fate of the universe? The everywhere is smooth question, again, is why? Where did that bumpiness come from, right? Can I write down a model that makes it seem totally natural that there would be these tiny fluctuations in that microwave light that end up giving me galaxies today? Expansion rate is more of the same. Why is it there at all? Why is it this much? How do we get that? And the same thing with matter. Well, what is it? It's something new, fine, we know it's there, but what is it? And all of these questions are ways in which, of course, we infer things that we can't see directly, right? That matter emits no light. Dark energy emits no light. We infer stuff that we can't see directly, of course, by what we do see. And when we use our physics hat to ask what kind of answers can we find for these questions, usually we ask, what is the particle identity of that stuff? Okay, so it's not what's here in this room, but what is it as a particle, as particle physics? And it's especially easy to illustrate what that means for one of those questions, which is the 4th question about dark matter. So most matter is something new. So what we'd like to do is uncover the particle identity of this stuff. So what does that mean? There are lots of ways that we know that dark matter is out there. In this picture, I'm showing you a little bit more detail of one of those ways. And that way is actually to just largely go and collect light again. So of course you can collect the starlight. That's what looks like stars in this image. You could also go and collect the light in other wavelengths. So there's a lot of hot gas in galaxies that emits very high energy light, X-ray light. And that gas, that hot gas, is shown in pink here. So there's all kinds of stuff that's gas, all kinds of matter that we do know what it is, right, that you don't just see when you see the stars themselves. On the other hand, you can go and ask, okay, but is that all the matter? And one of the ways that we ask, is that all the matter, is that we look at things that are affected by gravity, even if they don't emit light. So, for example, we can ask, how is light bent? Because gravity bends light. So what's shown in blue is what we get when we just ask, gravitationally speaking, where is all the matter? And you find that there's a lot more in this picture than what you would get if you just added up the starlight and the hot gas. So we know that's there. We see it in lots of different ways by the action of gravity. But we want to know what it is. And figuring out what dark matter is a lot like knowing for centuries that water exists, right? And knowing a lot about water. It's a fluid. You can see a canyon that water formed even if you don't see the water. If you can't see the water, you can hear it rushing by. Right? There are lots of ways that we understand what water does and what it is. But it was a long time before we knew what was the chemistry of water, right? What is hydrogen, what is oxygen, and those things are made of things like electrons and protons. It was a long time before we knew the particle identity of what water is. So that's sort of where we're at with dark matter. We have lots of evidence for what it is, how it acts as sort of a fluid, but we don't yet know what is the equivalent of the water molecules that makes it up. So physicists have had a lot of success with this type of thinking in general, right? After all, this is a very complicated picture. But I can narrow it down and say, okay, well, a lot of complexity there. But actually, everything in this picture is just made up of a few particles and a few fundamental forces. And there's nothing that says we've conquered nature more than making plush toys out of nature. I don't know. Okay. So we've had a lot of success. And based on that success, we have a lot of really good ideas about how to go out and answer these questions. And that's what we've been doing, and doing, and doing. And we still have these questions, which is a pretty interesting situation to be in. So what we've been working on for decades is to say, well, there's probably some particles that explain each of those. We can attack those sort of piecemeal. I mean, ideally, we'd have a framework where, the particle that do one, there's some way that it makes sense and fits into the same framework as the particles that do all of the others. And that's the way that we've been going about this. The fact that this works at all, this standard approach, is actually a really remarkable fact about nature, right? After all, I showed you that very complicated picture of a beautiful river in a beautiful canyon with a bunch of beautiful trees. And I said, oh, it's made out of electrons. How do I know that? Right? How do I know that? And the remarkable feature of nature is that it's possible to find really simple building blocks with pretty simple interactions and put them together to make a complex system. There we go. Okay. You're probably not impressed too much, because how do I actually do that, right? That's the hard part. How do I actually do that? And the other question is, how do I actually find that? How did I figure out that those simple building blocks made up everything in that complex picture? The way that we can do that is that sometimes, not always, right? Clearly not in that picture, but sometimes we can take just a few of these things and treat them as an isolated system, where I don't have to worry about all the complexities of the picture. I can just isolate a few things and see what they do. This has been the story of the success of physics, right? For example, it turns out we're really lucky that you can just go on a tall place and drop a few things, and the only thing that matters is the giant Earth and those balls that you drop from the tower to figure out the basics of gravity, right? The acceleration due to gravity. The nightmare of every introductory physics course, right, is these horrible wheels rolling down planes. Okay, but it's a wheel. It's simple. It's a plane. It's simple, right? The fact that we can build wheels and send them down planes and understand the motion is part of what makes physics work. And of course, we love to smash stuff together. Right? That's how we learn a lot. Our smashing has gotten pretty sophisticated. Right? We don't just smash billiard balls together in an introductory physics course, but we actually figured out how to smash fundamental particles together. So this is a picture from the Large Hadron Collider, where the billiard balls are protons that you put together in big bunches and speed up and send them violently circling around so that they crash into each other. And because you've worked very, very, very hard to make the system of protons simple and to control them very precisely as you send them around this ring, you think that you can figure out from the output if there's anything there that was unexpected. Right? You understood so well the initial state and how you put them together that if anything unexpected happens, that can be a signature of something new. So, the reason all of this works is that it's both simple and in some ways reductionist. Right? You can take some specific components with different identities. So this is a billiard ball and this is a billiard ball, or this is a proton and this is a proton. And I know very well what these things are when I have them in my two hands. And then I can smash them together and see what comes out. And we'd like that to be able to explain everything and to uncover the nature of hidden particles. So that's the approach that's been remarkably successful and that we'd like to take over to cosmology. And we try to do that, for example, with understanding where those inhomogeneities in the early universe come from. And I'm just going to show you one tiny equation to show you what it looks like. But basically what we do is we identify a couple kinds of billiard balls. Here's one. There's another one. And we write an equation for what those billiard balls are, what their properties are individually, and then we add the smashing part together. And we say, okay, suppose it went like this. Suppose I had this ball and I smashed them together. What would that do in terms of those initial perturbations in the universe? And does it agree with data, right? And if it's right, well then can I say that these billiard balls were what was there? That's what we'd like to do. So physicists have been so successful with this, sort of reductionist approach that we try this everywhere, and it's become really easy to make fun of us for it. So in the beautiful comics of XKCD, here's a really obnoxious physicist encountering a new subject, and they're like, it's not so bad. You've got some complicated system. Oh, sure, just model it as a sphere, add some little interactions, and there you go, you're done. It's not that hard. Come on, guys. So easy to make fun of us that the physicist doing this with cows has its own Wikipedia page. So, yeah. Okay. So why do people like to make fun of us? Well, because here we are, right? It's true. This is amazing that we can do physics this way. It's amazing that we can find out what we have. And yet, there are all kinds of things about the complex nature around us that we can't explain. OK, so what? What do we do? So, of course, the reason that we keep doing this is we get lots of things right? It has been incredibly effective. And even though I'm going to tell you about puzzles in cosmology, we get lots of things right. We've learned a lot about cosmology by doing this. So certainly, I'm not trying to say that we shouldn't do this. On the other hand, are there clues that cosmology is not a spherical cow? Are there clues that maybe there are some limits to this approach and that perhaps we should write down some equations that look a little bit different? And that's what I'm interested in. So I'm interested in the ways that cosmology is sort of different. And here are a few of them. One of them is that when I showed you those simple test systems, that collider was not simple. We went to a lot of work to build that collider. Even the billiard ball, not simple. Even the wagon wheel, not simple, right? You don't find those things laying around and get your physics intuition from the stuff that's there. We work very hard to build very simple systems that do very simple things. Out there in the universe, we can't go and manipulate that stuff, right? Now, we're very lucky that often we can find systems that are simple enough that we can treat them as if they're those balls or those wheels, and that's really fortunate. So the fact that we can't go and manipulate the universe, in some ways, a little bit of a red herring. Not entirely, but in some ways. On the other hand, there are some complications of cosmology that I think are more serious. One of them that we've been grappling with for forever, right, is that we can only observe this non-steady state system from right here and right now. There's no appreciable way that I can go to any other part of this diagram and make new observations, right? No way. And in a universe that's changing as much as this one is, that's a pretty interesting constraint. Another constraint is that we cannot see the whole thing. So we can't see the beginning. The light that reaches us is only from so far back, and beyond that, we got nothing, right? We got to do inference. We don't know what really happened. I like to call this the blinding flash of ignorance. We don't know. And we can't see beyond the edges, right? There's a finite distance out to which we can see, which has to do with how far light can travel and what the expansion rate of the universe is. That doesn't mean there's all there is, right? That doesn't mean that's all that was produced in whatever happened in this early time. We can't even see some stuff in the middle, right? Gravity does lots of interesting things where it makes these surfaces, these horizons that we can't see beyond. We can't see within, we can't see past. So there are lots of parts of the universe that we can't even actually see. And most of the interesting stuff here has to do with aspects of gravity that don't show up on the planet Earth. So the modeling that we do here is fundamentally different, and the successes that we have here is fundamentally different from what happens when we go out into the universe, where gravity on so many scales and in so many regimes becomes important. The way we typically deal with the fact that we're here and now in cosmology is that we do statistics, right? So I can go out and look at this patch of the sky and make some measurements, and make some measurements here, and make some measurements here, and start to paste them all together. And I can start to ask questions about the frequency of things that appear across the sky, right, and what the statistics of those things are. And the reason we think this works is that we think our place is not special. Right now, of course, the time may be a little special, but let's just say our place is not special. So when I look out, there's no conspiracy that lines up all the galaxies, in some pattern behind, away from me. My place is not special. And we articulate that by saying, well, if I think about structure formation, and this is a simulation of the early times of structure formation, and I zoom in on some part of this web of, clusters of galaxies, and I pick out of there some not particularly special galaxy, and then I zoom in on some not particularly special part of the spiral arm of this galaxy and find a solar system, and there we go, right? So we're not special. We're done. That's something that we sort of have to put in order to make our statistics make sense, right? Because if we were special in some way, we'd have to know which way in order to do the statistics. And how would we know which way? We've got one data point, right? One observation point. So we assume we're not special. OK, that's what we do. It works pretty well, but it doesn't work completely well. And again, part of the reason that we struggle a little bit with this is not only are we only observing from here and now, but there are parts that we can't see. So when we say we're not special, we also mean that the parts we can see are not special compared to the parts we can't see. And we have to somehow make sense of that. And for me, this really became important by thinking about the fact that the universe that we observe, again, is probably not all there is. So our very best models for what we think happened that generated the universe generate a space that's exponentially bigger than what we see. but is sort of statistically more or less the same. And we could be anywhere in that space. How would we ever know, right? The question is, does it matter? Does it matter when we try to understand what this spectrum of perturbations is? So how could it matter? Well, it could matter if there was something going on in the background that affected what was happening in the patch we could see. And it could just be statistical, right? It could be almost like there was a density fluctuation on large scales. And where there was a density fluctuation to make things more dense, then all of the structure was enhanced locally. On the other hand, if we were on a spot where it was sort of underdense compared to the big, giant blue circle, maybe the structure formation would be sort of suppressed. We'd have fewer stars, fewer galaxies. If we just want to make a model of what we see, we don't care, right? We're just modeling what we see. So whatever that background is compared to the mean, it doesn't matter. It's irrelevant. It's just the universe we've got. Most of the time, though, we think it's kind of funny to make a model that just stops at the edges of what we see, because that's not fundamental to the picture, right? It just happens to be the edges of what we can see. So we don't like that. It doesn't feel good. So we'd like to make a model that's the average over all of that and understand, is what we see sensible given the model for all of this and where we are? But you can see that if there's stuff like this going on, it kind of complicates the picture, because again, are we special is now a statistical question about what's happening in this really big space. So that's what sort of got me thinking about this story that I'm telling you. Really what this means is that everything that we observe is not isolated probably from the rest. In the models that we write down that do this, this is really some particle that has quantum properties that's talking to other particles that matters here. So everything that we look at, those pictures that I showed you, is a subsystem. And it's a subsystem in lots of ways besides just this one, right? It's certainly a subsystem from the point of view that some of the particles may not directly interact with normal matter except through gravity, so that's like that dark matter, right? We've tried so many times to go out and hit the dark matter with other particles and get it to sing, right? And it doesn't do it. We can't find it. We don't see it. It could be we haven't looked in the right place yet, or it could be that interaction is so weak that the only way we're going to detect it is always through gravity. So that's sort of like a way in which what we observe is a subsystem, right? We have to grapple with what does it mean to only see something that talks to us through gravity. Of course, we can't see things at very, very high resolution. So some structures, very, very deep in the description of what the universe is doing on small scales, may be so far down that they're too tiny for us to access. So that's a sense in which things are hidden. And the thing that I'm also particularly interested about is that some parts of the horizon are hidden because gravity makes walls that we just can't go past. Why does it do that? It forces us to make observations that we know are, can be sort of talking to parts of the universe we can never observe. So when the interactions with all the rest of the stuff matter, does that change how we frame the problem? Right? It's a different problem from, I'm sure what this is, I'm sure what this is, I smash it together, I get the answer. Now, in some ways what I'm saying, just as we've all dropped a ball or rolled a wheel, and that's so familiar to us that we can look at those systems and do physics, this picture is also so familiar to us, right? Because this is what most of our experience of the world actually is. I mean, to be human is to be a partial observer. And most scientists who aren't particle physicists are also partial observers. So this is a beautiful picture of fluorescent light on a flower, UV light emitted by a flower, emitted by the nectar of the flower, which of course we didn't know until somewhat recently that flowers and insects and various other animals have signals in light that we don't see, but other parts of nature do see. So what does that mean? What is the system here? If you look at the flower and you know it emits in the UV, and you're like, oh, okay, why does it do that? It's pretty hard to answer that question without looking at the rest of the system that's relevant for that flower, so all the pollinators, for example. But where are the boundaries? Where are the boundaries? If I consider the flower and the nectar and the pollinators, I should consider the earth, I should consider the clouds, I should consider perhaps the honeybee keeper. Where are the boundaries? So this notion of systems that are intimately connected to environment, where the environment really matters, is a very familiar one from the way that we do. We observe most of that complex natural world around us. In physics, we do have formal techniques for dealing with systems like this. We usually call them open systems, meaning that I can't describe everything right here and wrap it up in a nice, neat ball. There's stuff I can't quite observe, so I have to talk about what happens with the environment. And usually what we do is we try to formally parameterize everything that this environment could be doing and interactions between the system and the environment on what happens to the system itself. None of that we can know for sure, but we can say, oh, well, maybe it's of this type, maybe it's of that type. What's the difference between those systems? Sometimes open systems are super easy. If you put ice cubes on a very large hot sidewalk, no surprise what happens, right? The ice cubes are the system, then there's the environment of the hot sidewalk. That's pretty easy. This is a physicist's cartoon. This is my spherical cow, right, for that picture. It has a very obvious and a very boring end. We're done. Ice cubes have melted. Everything's very hot. We're done. Oops, that went too fast. That simple picture of open systems doesn't seem to be what's happening in the whole universe, right? Especially because I told you this story about how we're not special. We zoom in, we zoom in, we zoom in. We find the planet Earth. And we find that the behavior of some systems is, frankly, sort of shocking. What is this, right? What is this? It's very interesting. So the math is easy for systems like this, where we have the ice cubes melting, right? It's a very simple picture of what's happening in system and environment for systems like that. But we've got this. We need to describe subsystems that are doing very, very different things, including things that look absolutely nothing like ice cubes melting. So what is the math for that? What shall we do? So what we'd like to do is to have a physics model that's simple, right back to the simplicity picture. There's no way I can describe red pandas. I want something simple that I can write an equation for, but that has some of the properties of this, so that when you look at what subsystems are doing, it's very diverse. They're not all doing the same thing. They're not all just ice cubes melting. And how can I think of that collection of systems and model it where I know that the environment matters? And I know that the environment of this is related to the environment of that. I mean, this is way too complicated for me, right? But the environments are related because it's all a giant system. I can see this part and this part, and this part is the environment for this part, and vice versa. More like the picture of the pollinator. So how can I make a model for that? And in some ways, this is like the reductionist revenge, right? Because it turns out I actually can write down a pretty simple physical system where I can ask these questions and formulate them in a really concrete way. And this is laboratory quantum systems. They actually provide the tool and the model that allows us to ask some of these questions in a very precise way. So this is an artist's rendition of two quantum particles that are entangled. So this is the hallmark of what we all know about quantum mechanics, right? Entanglement. That's the thing that's different and unique about quantum systems. And what this picture is trying to get at, with quantum particle here and quantum particle there, well, I don't know if it's what trying to get at, but this is what it means, what entanglement means, is that neither of these particles independently really has an independent state. This is not, I picked up a billiard ball, you picked up a billiard ball, and we smashed them together, right? In this picture, those billiard balls are really actually the same system. What does it mean they're the same system? Well, partly it means that I had to give an extra label to those billiard balls to tell them apart. So I had to say, you hold that one over there, I'll hold this one over here, right? And then you've got one, I've got the other. Those are the subsystems. But that needed an extra label. And then if you've got one and I've got one, and I make some measurement on my billiard ball, the fact that really they're not independent systems shows up in the fact that some properties of the billiard ball over there will be different. They weren't independent systems. The thing that makes this really interesting is that depends on how we defined our subsystems. If we'd chopped up those balls a different way, they wouldn't have necessarily been entangled. So quantum systems have, at their heart, this whole interesting picture of how do I take a big system, and I chop it up, and I ask, what are the correlations between the part I can measure and the part I can't measure? And what if I chopped it differently? What are the correlations between the part I can measure and the part I can't measure? And if I then start to model the dynamics of this thing, how does it matter that it's correlated with the rest? This is really quantum correlations. This is the fun part between what's observed and what's not observed. And now this probably starts to sound like stories that you've heard about black holes, for example. Right? What happens if you have entangled particles inside and outside of a black hole? This is one of these boundaries that gravity gives us that we cannot do anything about. I am not allowed to scoop up the matter from inside the black hole, put it over here, and say, oh, look, that's my system now. How do they interact with each other? I can't do it. Gravity tells me I can't do it. So I absolutely need a way to understand what happens when I want to describe a system that's open, that can be quantum correlated with stuff that I can't measure. It's really actually at the heart of this story, too, because again, this is really, all the particles that we model in nature when we try to do cosmology, those are really quantum. Now, the observations we make are very classical, so I'm not saying we're going to go measure interference between galaxies. The observations are very classical, but the particles themselves are quantum. And so when I try to write down these particle physics stories where I want to do inference and figure out what those particles are, it's really a quantum inference problem, and I need to take all the complications that come with quantum inference with it. What's great about this is that I told you in cosmology we're sort of stuck. We absorb here and now. We can't go out and make the simple systems that we're then going to use to test our theories. That's a problem. What's nice about this is that understanding quantum systems, where there are correlations, and say I only observe this part of the system and I want to talk about its evolution, that does happen in the lab, absolutely. And that's something that we can go and manipulate and make experiments on and test whether our models are making sense. And in fact, this is a really active area of research because, of course, quantum systems, incredibly important for lots of reasons, right, including computing. So figuring out how to isolate systems and what happens when the systems talk to other quantum systems is a big deal in general. But that means there's data, and that means there are experiments. And that means that if we come to this with questions that a cosmologist would ask or a particle physicist would ask, those questions are different from what somebody who wants to build a computer would ask, or from somebody who builds a material in a lab would ask. And so we have a chance to actually find data about how to build good theories by looking at what happens in the lab. So I've been putting these two things together, this sort of out of equilibrium nature, right, and the funny subsystems that do funny things, and the open system picture together. And I'm talking about those two things together because when you have that simple picture of stuff melting, all the subsystems are pretty much the same. It really doesn't matter which one you pick up, right? Well, you pick up a little piece here, a little piece here, a little piece here of a hot gas. They're all the same. Doesn't matter. Where this story gets interesting is where distinct subsystems tell different parts of the story, right? They contain different information. And by taking those partial observations and putting them together, that's where you start to reconstruct something that's really new about the whole system. And again, that's what most scientists do all the time, right? They don't know which amino acid is actually important and how it got there. They pull the observations that they can, put those together in a complex system, from the different information of the different subsystems, and put that together. In physics, we have a version of that, which we can do using quantum systems. So I really think these things go hand in hand. OK, so I want to compare then these sort of two stories that we have. One is the story that I've worked on most of my career, that everybody that's been doing cosmology for the past 4 decades has been doing, which comes out of the success of particle physics and these really good ideas that we've had by thinking about what are the fundamental particles in the universe. But that story is a story that's very much a closed system story. We usually assume we've got it all in hand, and we know, or we can tell a story about what those components are, and then see if it works out, see if we can get something that describes the universe. We know the components, they have their distinct identities, we bring them together to interact in some way, and if we were really, really good, we could discover the properties of those complex systems based on the properties of the components. On the other hand, we have a different view, which is both open, meaning I have to ask which parts of the whole can I see? That's the first question I have to ask, not let's assume I have these parts and I know what they are. But I also take a different approach to what the complex behavior is. This is actually something that has a key, like a buzzwordy phrase in physics, which is called more is different, which got famous in the 70s when physicists who aren't particle physicists look at big collections of quantum particles in the lab and they go, you know what? It's really different, the types of behavior you see when you put a bunch of particles, like quantum particles, together. And this has been a really important theme of much of physics over the past several decades. But it hasn't quite percolated into aspects of cosmology and particle physics as much as it might, partly because it wasn't clear what the connections were. It's possible that we're starting to have a connection, and really what we need to ask in the context of cosmology is, when this complex behavior that we see, when does that tell me something about the structure of the parts, right? So I should take as fundamental or as important key knowledge the fact that the universe gives me this diversity of structures at late times. That is a feature of the universe I've got. That's something I really need to explain. And that, not just let it sort of roll out as we do with the Earth from electrons. So these are two different perspectives, and I'm particularly interested in seeing what happens when we address cosmological questions from this point of view, and see if that gives us any new insight on those very difficult and long-standing problems. So coming back to this picture one more time, we have these facts. The universe is not in a steady state. It's nearly smooth everywhere, but not quite. The expansion is accelerating, and most of the matter is something new. We've known these things for a very long time. What I wonder is if figuring out the answer is partly comes from rewriting our math framework for this that really embraces the fact that the part of the universe is hidden, and why is it hidden, and how did it get hidden? And I think that's especially true with these questions here. And so my bet is that when we understand more about the answer to these questions, we will have created a theoretical framework for cosmology that at its foundations finds a very natural home for these open quantum systems. And at the same time, it embraces this out of equilibrium nature. So it gives us these ensembles of systems that can have a diversity of behavior in the subsystems, and that's how we extract information about the whole. So that's what I hope is true. What I love about cosmology, though, is that the data will tell me if I'm wrong, right? It will tell us how to get on the right track. And both the laboratory data will tell us that, and the cosmological data will tell us that. So I look forward to the universe telling me I'm wrong for the rest of my life. OK, I'll stop there. Thank you for your attention.
Thank you so much, Sarah, for that fantastic talk. I have a lot of questions, but I also think we'll have a lot of questions from the audience. So if you have a question for our speaker, please make your way up to the microphone here on the stairs. As people make their ways to the microphone, we've had a few questions rolling in online, so I'm going to kick it off there. Can you give an example of how a quantum system might tell us something about cosmology?
Yeah. OK, good. So of course, this line that I'm drawing is a speculative line, and it's a distant line. But one of the things that you might imagine is that if you look at a collection of subsystems that are doing something surprising, so they're behaving in an out of equilibrium way, you might say, well, I know the laws of thermodynamics, so I know, of course, that entropy has to either stay the same or increase as I go. And if it looks like these systems are doing something special where entropy is kind of decreasing, there must be something going on in the environment where entropy is increasing. So it's a way that you might imagine that looking at local behavior tells you that there has to be something bigger, something more global, that supports that particular behavior of subsystems. So it's a way, instead of thinking about cosmology as a background with little perturbations, you think instead of what's the behavior of the subsystems, and that tells me what has to happen as sort of a surrounding or enveloping bath, if you like. Now, you can think of that classically, but it's more interesting to think about it quantum mechanically, where we can make all of those notions that I said actually precise, and precise for the systems that we're interested in. So that's one.
Nice. All right, go ahead.
Thank you very much for the talk. That was really, really interesting. I wanted to ask about how this might tell us about the cosmological constant, which has been a thorn in the side of cosmologists for a while, as I understand, and whether this line of analysis could tell us that the cosmological constant might be due to maybe an emergent property or because of interactions with some open system that this is a part of.
Yeah, thanks. I mean, in some ways, and again, this is rampant speculation, right? But in some ways, that's sort of what I was alluding to a minute ago, that we don't understand this apparently long wavelength, infrared behavior. We don't know where it comes from, and efforts to model it as a particle, I don't know. Maybe I'm not so impressed with the results. So it'd be nice if there was indeed a different way to understand how that had to be there to support some of the structure that we see. And I really don't mean that in a very hand-wavy way. I mean that I want that in a very precise thermodynamic way, right? That's the story that I would believe. And we don't have that story, but it'd be interesting if we could tell it. Yeah.
Thank you very much.
Thank you. All right, I've got another one here from online. If there's any more in the audience, please make your way up to the microphone. About halfway through your talk, you said that the time we are in might be a bit special. What did you mean by that?
Yeah, well, I mean, I guess I meant the fact that this picture is changing as a function of time, and the fact that we live sort of now when the expansion of the universe is starting to accelerate, and in this era where we have all these galaxies, I don't know what to make of that, right? In some ways, it is a special time, but we have, do we have to live at that time? Because that's where observers are. You get into all these tricky questions, right? But it's not clear if it's a special time or not, and how we handle that in our statistical model.
All right. Oh, we've got another question. Please, go ahead. Yep. We've got time for more questions. I wanted to ask another one that came in from online in terms of the kind of quantum systems that you're talking about. Is this something that, like, in a laboratory experiment, we could directly measure something about cosmology?
Yeah, I mean, again, I think of these models as indirect laboratory tests. So we want to make systems that have analogous properties to what cosmology is doing, right, in order to sort of ground the theory that we write down and see if that theory makes sense once you then extrapolate it to stuff that we can't observe. So I think of it as more indirect, where we'd be able to set up an experiment that just tells us if the equations that we're writing down make sense and if they predict the behavior that we expect. So more of a test of an analog system in the lab.
Fantastic. Go ahead.
So, because of your talk, kind of gave me an aha moment. I've never thought of this before. Was dark matter and dark energy around before the Big Bang, or was it a product of the Big Bang?
So let me first say what I think of as the Big Bang, because people use this word in different ways. I think of the Big Bang as the era where whatever energy was present in the universe at earlier times got dumped into the matter that we have around us. So it really started off, the hot universe in the matter we know, and the universe expanded. So part of your question, I think, then is, at that time, was that matter present? And I would say yes, it was present in some form. And what happened is that as the universe expanded, the importance of that matter changed. So the dark energy was there, and we should understand how it was there, but its importance was sort of minimal in the early universe, and it became important later.
Okay, lastly, could it have been a catalyst to start the Big Bang?
I think I don't know the relationship between those components and what the event was that caused that transfer of energy. Certainly, people write down models where, in that transfer of energy, they account for transferring energy. It's sort of the creation of the dark matter particles. So there could be, sort of a common origin, maybe more than a catalyst.
Okay. Thanks.
Yeah.
Great. All right. Another question from the audience.
I happen to be a Buddhist monk, so I was reading something from All Knowledge System, and it has a theory which is similar to a finite universe. And then it got me to thinking that could be living inside a big black hole with a finite event horizon, and that's the event horizon of 13.5 billion that we are seeing. My question is that possible to come to that sort of a conclusion, or at least as a theory, purely with math, or do you need some sort of a observation from the outside universe? Can you do it completely theoretically?
So, the way that we test things completely theoretically without observations is to check for consistency. And so if you're able to write down a set of equations where everything is sort of self-consistent and no observation can tell you that there's anything against that model, then that's sort of what it would mean to show that, theoretically without any sort of data. I guess I don't know what it would mean to get data from the outside, because we can't by definition. So you'd look for theoretical consistency there.
All right. There are no more questions from the audience. Please join me in thanking our speaker again, Professor Sarah Shandera.